Thank you very much for coming and for your interest in blockchains and oracles and smart contracts. So today we're going to be talking about smart contracts, the need for them to connect to useful resources, some recent news about Chainlink, and what we plan on doing next. So I think it's important for us to get on the same page about what the fundamental problem is, because that'll give us some clarity about the value we're trying to provide. So the fundamental problem is one where smart contracts can't connect to data. So if you can't connect a contract to a piece of data, you can't write it about that piece of data. So this fundamentally means that all the derivatives, insurance, supply chain, trade finance, all of those applications have events. They have market events or real world events that those contracts need to be written around. And the way that smart contract systems like Ethereum, Hyperledger, or really any other real smart contract network works is that they're simply unable to speak with these data sources. Since they're unable to speak with these data sources, we have a situation where we now cannot build the types of contracts that we find interesting. We feel this problem extends to probably 80% of the smart contract use cases that provide real world value. So we think right now the entire space is in a stage where only about 20% of what can be done or can be built is even possible, because that 20% relates to tokenizing assets and then moving around those tokenized assets between different parties. The other 80%, in our opinion, is the ability to build contracts that react to events. Market events, real world events, trade finance events, all kinds of different events related to the important points that a contract would be written about. So this is why this problem is particularly important. It basically puts us in a position where if we have this problem continue, we can't build the vast majority of contracts we want to build. And it's once again a fundamental problem to all networks and all chains, the fundamental inability of the smart contracts on these networks to talk to any external data feed because of the security model that actually secures the smart contracts. Now, to really understand the significance of this and what I think solving this problem might result in, I think it's useful to look in this in a more historical context. So historically, the way that people have looked at smart contracts was it began as basically Bitcoin multi-signature. In the early days of Bitcoin was considered programmable money. And programmable money was the exciting idea that got a lot of people into blockchains and smart contracts. This idea of programmable money was in fact what also got me into the blockchain world. Then around the years of 13 and 14, you had the appearance of protocol smart contracts. This was when if you needed to build a smart contract, you couldn't write it yourself. You had to contact a protocol developer. They had to write it, and they had to put that smart contract into their protocol. That took anywhere from 3 months to over a year. And so if you wanted a new smart contract type, you needed to get in touch and they needed to add another piece to their protocol. Then what Ethereum did is it greatly expanded the functionality of smart contracts. So it took us from these protocol smart contracts where you had to show up and have a 3-month conversation, a 3-month release cycle, and then another 6 months of testing, and then who knows what else, to you can sit down in a week, write a contract, publish the contract about whatever tokenized asset you want, and in whatever way you want that asset to work, it'll work that way. So fundamentally, this huge increase in features created the large explosion in value we've seen over the past approximately 2-3 years, right? This is essentially where this explosion in value came from an increase in features that allowed people to generate smart contracts that represented a specific category of contracts, and for them to generate those contracts in a reliable, easy to create, and easy to consume manner, right? So this explosion in features created a huge explosion in what people are able to build. We feel that fundamentally, if we think about the contracts that smart contracts as an entire class can replace, we think that scriptable smart contracts that only do tokens are going to inevitably move towards all other contracts. But to move to all other contracts, they need to know about the contractual events that those contracts are about. So fundamentally speaking, the next version of smart contracts, in our opinion, is the one that's able to fundamentally interact with all these other events. This capability basically takes us from scriptable contracts that focus on tokenization to all the other contracts. Futures contracts, various other derivatives, insurance contracts, trade finance, those types of things. So what I'll be talking about is, how do we make that capability possible, how we're doing that, and how we're going to continue doing that. So fundamentally, the way to solve this problem is through something called blockchain middleware. Blockchain middleware basically provides you with a piece of software that sits between all of these data sources and the contract, providing it with that data, so the contract can now know about an event and can now be written about that event. Likewise, blockchain middleware provides connectivity between the contract and various payment methods, because commonly contracts are about transfers of value, payment, and so you want a middleware to be able to both trigger your contract and to enable your contract to work with various payment systems. And then the third, more long-term, more far in the future idea is the ability to trigger contracts or events in other chains from your contract. Now, we've been building this capability for years, and the fundamental idea that we've come to that's particularly kind of key to grasp or to realize, in our opinion, is that the value of a smart contract is based on its weakest part. So basically, if you're going to expand what smart contracts do outside the secure system in which they already function, then you need to do it in a way that maintains their reliability. If you expand what that contract can do, but you break its security or trust guarantees, then it's no longer useful. It's no longer any better than the contracts it's replacing. So the fundamental core value that a blockchain middleware needs to provide in our space is the ability to connect with all the inputs and outputs that a smart contract needs, and the ability to maintain the security and reliability of the smart contract end to end. So this end to end reliability is where blockchain middleware differs very greatly from any other type of middleware or anything else that connects systems. It needs to provide as much of the same level of guarantees as it can to maintain the fundamental value of a smart contract, which is its security and reliability. So at the end of the day, we've also looked at how not to do these types of things. And the fundamental idea that initially seems intuitive, but we think is fundamentally wrong, is the use of a centralized single oracle. So the use of a centralized oracle means that you arrive at a place where you have a multitude of data sources, you have decentralized computation that's actually executing the contract, but you have a single oracle. This single oracle basically creates a single point of failure, which is exactly the thing that smart contracts successfully avoid, right? So smart contracts are considered unique and useful because they successfully avoid single point of failure scenarios for tampering, for security reasons, for any kind of censorship reasons, whatever reasons you want to name. The fundamental value that smart contracts provide compared to their centralized competitors is that they avoid this single point of failure issue. This is what people call tamper-proof, or what fundamentally we would say is the value of decentralization. So fundamentally speaking, we don't want to be in a position, if we want to maintain the end-to-end reliability of a smart contract, and we want to expand its features, and we want to do both of those things at the same time, we're going to on those two assumptions, we're going to logically arrive at a point where we say, okay, if the fundamental assumption of smart contracts is decentralization, perhaps we need to arrive at a decentralized method of providing these trigger and input events. So fundamentally, that is what Chainlink is foundationally built on, in addition to a few other approaches. It's the ability to decentralize this oracle mechanism, and then once that's decentralized, you can successfully begin decentralizing the data origin level. So as you seek to make a smart contract more reliable, you'll fundamentally move outwards, right? You'll consider the smart contract state more or less reliable on its many network of nodes, then you'll move out to the mechanism that's actually triggering it, and then you'll probably move out to the data feeds. So I'm just going to run through two quick examples to hopefully put more of this in context and provide slightly more clarity on exactly how this looks in a more practical context. So the first example is a very simple derivatives contract, something called a future. Futures need to be settled, commonly daily. To be settled, they need prices. They need to know the price, whether a certain price has been reached, what price has been reached. And if you fundamentally want to build decentralized cryptocurrency derivatives like futures, and you want to call them reliable end-to-end, you need decentralized computation, which reliably holds the contract and creates the state changes. And then you would also need a decentralized method of triggering that contract. In this example, this is something you can actually build today using our system. It's something many people today have built using our system. It's the ability to do a decentralized computation in whatever network you'd like, to get the data to the contract and to get it from multiple sources. Likewise, after you've done the necessary computation for your derivatives contract, you then need to pay. This is the next stage where middleware is particularly important. It provides you the ability to pay out the contract wherever you like. So instead of us having to force people to use a payments system that we need them to use because of technical constraints, we can have a piece of software that allows them to reliably pay out in the systems that they need their customer to get payment in, right? So this is the second very clear kind of piece of value we see people needing and using. The next example is a bit more complicated. It focuses on a multitude of inputs. So the example is about frozen goods insurance. So let's say you're shipping frozen goods from another part of the world, and you need a guarantee that the goods have remained frozen in order for them to be purchasable, in order for them to be insured, in order for the contract that you have about these goods to be valid and for you to receive payment and so on. So fundamentally speaking, this is actually a contract we've worked on even many years ago, even now with some insurance companies. So fundamentally speaking, we think this is actually a very, very real use case that intersects between both supply chain and insurance. So you can have the container GPS data going in, then you need the data about the temperature in the container, you need the data about the security of the container, such as that it wasn't opened in transit. Then you can get data about customs release, that the goods have arrived at a port and cleared customs, and then that the goods have been delivered to the warehouse of the purchaser. So all of these inputs individually need to be put into the contract. They need to be put into in a secure way. And once they're put in, now you can have a contract of this type. If you can't put them in, you simply can't make this contract. Likewise, in this contract, the next step in this example is the ability to pay. Once again, the ability to pay possibly multiple parties, a single party, in multiple different methods. So fundamentally, this is a clear example. The two clear examples are, one, the need for decentralization when you need to make a highly reliable input, and the other one here is one of multiple inputs. So fundamentally, what Chainlink focuses on doing is providing this multitude of inputs and providing it in a secure manner. So there's two key parts to that. There's the creation of the many inputs, and then making sure that as they're provided, they retain their security and make the contract reliable. Now, we've been working on solving this problem for some time, and today we're glad to announce that we've made substantial progress. We've had a lot of users come to us and start using and working with us, and today we're glad to say that we're We're able to launch on Ethereum Mainnet this month. We've been able to successfully complete 3 security audits without any really critical issues being found or remaining. So fundamentally, from a security point of view, we feel that we're in a position where we can go live on the Ethereum mainnet. And the significance of this, and also in relation to this, there will be more details in an upcoming official, more detailed blog post next week. So the fundamental value of this, in our opinion, is that we'll be able to provide decentralized oracles for the existing dApps on Ethereum and the many, many dApps that aren't on Ethereum yet. In our opinion, from our experience working with many decentralized application teams, a lot of the dApps that are very interesting, possibly even more complex, more interesting, a lot of them are going live this year. And so there is a subset of applications already live on Ethereum and a certain subset that's going live. Here on this slide, this is a picture of some of our announced users and partners. Some of them are already live, some of them are going live, some of them are data providers. So we basically feel we've reached a point where we have a substantial enough amount of security guarantees. We have enough data providers that want to sell data directly to contracts of the type that contracts want to purchase. And we have a substantial amount of contracts that want to purchase that now or in the near future. The second really significant point about being able to go on Ethereum mainnet is that it puts us, it's a significant step towards us being able to support all of the EVM Solidity powered networks. So there are a lot of EVM Solidity powered networks out there that use the Solidity smart contract language. Tron, EOS, in our case there's one called Nakachain. There's a whole bunch of different chains with various variations that use the Solidity smart contract language, and they're able to, well, now they'll be able to consume oracles. So our goal here is initially to go to Ethereum mainnet, provide the necessary decentralized oracle capabilities there, and that will put us in a good position to be able to provide those same capabilities on all the variants of EVM Solidity powered networks. Now, like I said, there will be more details in an official blog post next week. And fundamentally, I think what's useful now is to kind of look at the next steps beyond going live on Ethereum and just look at some of the goals that we hope to reach. So fundamentally, I think the right way to look at Chainlink is as a large collection of inputs and outputs. So fundamentally, what we're doing is we're making a large collection of building blocks available. The right way to think about building blocks is the way they already exist in like the web world. In the web world, you have something called APIs. Those APIs get combined to build applications. That's how applications get built. So for example, if you wanted to build something like Uber, you would need a GPS API to tell you where the user is, an SMS API to message them, and a payments API to pay the driver, right? Without those building blocks, you couldn't build Uber. Fundamentally, that's the situation smart contract developers find themselves in today, and fundamentally, that's the environment we want to take them out of. We want to take them out of the environment where they can't build their use case or their more complex contract and into an environment where they can write their core code in a few days, spend another day or two connecting to the relevant inputs and outputs, and within a week, just like web application development, be able to launch. Fundamentally, what this means is creating a marketplace around, whether that's an on-chain marketplace or off-chain marketplace, basically an evolving marketplace that allows developers to reliably and easily purchase these inputs. That means the creation of pre-made inputs. It means taking specific APIs, wrapping chain links around them, launching hundreds of those chain links and providing them to those developers so that they can then combine them into the applications that provide 80% of that value that I mentioned. The next large goal that we have is the support of pretty much all the smart contracts that provide value that we can reasonably support on a reasonable time frame. So our goal, that's what I mentioned earlier, our ability to support EVM solidity-based contracts on something like the Ethereum Mainnet will then allow us to support the EVM solidity-based contracts on other networks, and then we'll be able to go beyond to various other networks, Hyperledger, any number of other systems. So fundamentally, the second goal that we have going forward is the ability to support multiple chains. Now, there's two pieces of value here. One piece of value is that the sellers in our network can sell to multiple chains without having to integrate with multiple chains. The second piece of value, which is rather immense, is that the enterprise users, or the users that don't want to pick a winning blockchain, don't necessarily need to pick a winning blockchain. They just need to get their system compatible with blockchains in general. If they can have a middleware that connects their system to all the different blockchains and turn their enterprise backend events into blockchain events, and then turn their blockchain events back into their enterprise backend events, they fundamentally don't need to pick a winner. They just need to get their systems to the point where they can interact with blockchains. So this is the second reason why it's particularly valuable that we're able to support the chains that both people on the public chain side and the enterprise application side would want to use. The third and possibly most important dimension on which we need to excel is the creation of the most secure oracles possible. We do this through a defense in depth approach. Defense in depth is considered probably the best way to approach creating a secure system. It's the layering of multiple security approaches on top of each other. In our case, we layer on decentralization, trusted execution environments, and multiple other approaches, some of which are in early stages of implementation, some of which are in later stages of research and early stages of research. So fundamentally, the goal for us is to provide a large collection of pre-made inputs that people can combine into great applications, to support all the chains where people would want to use those inputs, and then to make sure that those inputs, as they're growing in number and as they're expanding in both what they can do and where they're offered, that they maintain their security through a security model that doesn't myopically focus on a single security approach, but combines the best security approaches into a defense in depth approach. Fundamentally, going forward around these three goals, essentially this is how the teams in Chainlink will be structured. They'll be structured around a Chainlink growth team that will expand the number of inputs and outputs, the Chainlink integration team, which will integrate with multiple other chains, some of which we've announced, some of which are going to be announced, some of which are large enterprise chains, some of which are private, public, various chains. So fundamentally, the integrations team. And then there's the core Chainlink team, which focuses on maintaining the security of the software and the security of all the approaches that we recommend people use, so that all the inputs and outputs on all the various chains remain secure. Now, fundamentally, I think if we can do these three things relatively well, and we do them over the period of time that smart contracts begin to need more and more inputs, and we are the largest source of inputs, we support the places where people want to consume those inputs and outputs, and we provide those inputs and outputs in the most secure manner. Fundamentally, we're basically risking that people don't want to consume them. So the fundamental question is, do people want and need to consume these inputs and outputs to build the contracts that we think provide 80% of value, such as the derivatives industry, insurance, trade finance? And if we provide them these inputs and outputs and they do want to build those contracts, then fundamentally they will have to consume them. And from just a logical point of view, they'll want to consume the most secure ones, because the whole space is based on security and reliability. So to provide slightly more context in our defense in depth approach, I'm going to talk about how we're layering on decentralization with trusted execution environments. These two trust models are usually considered mutually exclusive, so they're usually considered that you choose one or the other, but we're actually going to show how you can combine them and provide a greater degree of security for the generation of something like randomness, which can power a large and growing sector of the current blockchain ecosystem like the gaming industry. So fundamentally, to achieve this goal, for years now we've been working with IC3 and Cornell and the folks that have made TownCrier. Last year we successfully acquired TownCrier. TownCrier is the longest running, I think probably first and so far most secure use of trusted execution environments for the delivery of data to smart contracts. It's been working in production now, I think, for over 2 years, and it's it's something that we've worked on with them for years, and that we're glad to include into Chainlink. I'm just going to quickly run through what that means. So fundamentally, what this means is that in addition to decentralization and a multitude of inputs on various environments, you now have the use of trusted execution environments. Trusted execution environments, they lower something called the trusted computing base. They essentially create less places where people can attack your software. Fundamentally, they isolate the software from the operating system and the most common places where people get into software to create malicious activity. Fundamentally, TownCrier applies this technology to the retrieval of data, the verification of data being retrieved from the right source, and the forwarding of signed data onto the relevant contract. The value of this in our case is that data retrieval and and computations around the data can now be protected even from node operators themselves. So this means that even Chainlink node operators within our network of Chainlinks, they cannot know what they're computing. They cannot stop the proper retrieval or publishing of data. All they can do is turn off their publishing of data, which makes them immediately disqualified as future node operators. Likewise, it provides confidentiality so that those node operators can retrieve that data privately, compute it privately, and send it on privately, so that even the node operators providing data to your contract don't know what your contract's about. And then the management of credentials for payment, probably credentials or logins or passwords that send money, you can now house those in a more secure environment. Fundamentally, one of the first places where we see something like this theoretically providing value is lottery contracts and various other gaming contracts. They function on the basis of randomness. So randomness needs to be delivered to them for them to decide who wins. They're an extremely simple contract of I need one input of randomness. That input is computed against my code, and I decide who wins, maybe millions of dollars. So that input is obviously very useful for the contract. It's also something that adversaries would want to attack to game to acquire the data. Fundamentally, what we can do is we can run the randomness in the Chainlink. We can derive it in this secure environment. We can then give it to the contract. And in our case, what we can do is we can take this greater degree of security and decentralize it. So our goal, once again, is to provide a greater degree of individual security, but then apply fundamental ideas about decentralization to increase the reliability of this randomness. So instead of attacking a single oracle, making it a single point of failure, even with the most secure approach, you now have multiple sources of this data, and this lottery contract is now far more secure, can hold far more value, and is therefore much more reliable. Likewise, it'll need to pay, which is what middleware will be also very useful for, and these are the fundamental, so this is the fundamental value we seek to provide. We seek to provide these critical inputs and outputs. We seek to make sure that they arrive securely, and we seek to provide them in all the places people need to use them. We're thrilled about going live on Ethereum Mainnet, and we plan to be launching on other networks and launching a multitude of different inputs and outputs, both as Chainlink and with the help of the community. And we're thrilled to be going forward and making this what we feel the next step in how our space delivers value, a tangible, real-world, immediate possibility. So thank you very much.